All right, good morning, everyone. We want to finish up Copernicus, and I just want to backtrack a little bit because we rushed through, I think, a very important point that I rushed through a very important point. So let me try to make it again. I'll do a better job. Why is it so important? Because of this great quote that we have from Copernicus's letter to the Pope. Get it up here. If the motions of the other planets are correlated with the orbiting of the Earth and are computed for the revolutions of each planet, not only do the phenomenon follow therefrom, but also the order and the sizes of all the planets and spheres and the heavens itself are linked together, that no portion of it, anything can be shifted without disrupting the remaining parts and the universe as a whole. This ultimately is his strongest argument to the Pope. He has very technical mathematical arguments and explanations and demonstrations in the book. But if you want to look at what is his best selling point to the educated world at large, that's it, that sentence. And I wanted to demonstrate that with the use of the calculation of the orbits to show that once you buy into this geometry of his, very fundamental measurements that have been known for thousands of years dictate what his system must look like. He does not have the kind of dials and buttons and wheels that he can turn and fiddle with the way the Ptolemaic system has been used for over 1,300 years. He's saying, I don't have that in my model. My model is either right or it's wrong, given the measurements that we know in the sky. Everything comes from these fundamental measurements. So I wanted to demonstrate, to show that. And I think I rushed through this. These first two slides here is about being able to compute the actual time going around, the periods of the revolutions of the planets going around the sun. And this is a nice piece of mathematics that we skipped. Here is the pretty formula for the period of a planet given the synodic period and our period. And you can go ahead and little pretty algebraic equation to compute that. Again, the synodic period is nothing mysterious. It's just the time from, let's say, an opposition to the next opposition, something that we can directly measure here from Earth. When is the sun and the planet on opposite parts of the sky? We'll wait for that to happen again, when the planet is directly overhead at midnight. There's nothing mysterious about measuring that. For example, the synodic period of the moon would be from the full moon to the next full moon. So here is an example of a measurement that we have been known for thousands of years. Given his geometry, he's able to calculate the true period of the planet's time to go around the sun. And there's the little demonstration that we skipped, giving these results for Mercury and Venus, 88 days and 225 days of their orbits around the sun, and the similar calculations for Mars, Jupiter, and Saturn, giving these. And these numbers are very, very accurate. The time it takes for the planets to go around the sun, Mars is 1.88 years and Jupiter is a little more than 11 years, etc. These are very accurate measurements given his geometry. And in fact, they are very accurate measurements given the real world. So here's an example of, many, one cause and many, many effects. From his geometry and the simple direct measurements of synodic periods, he's able to calculate the true periods, time it takes to make one revolution around the sun. Here is the distance to Mercury and Venus. Very, very nice piece of geometry. Again, it comes from a simple measurement. This is the maximum elongation of the planet. This is either Mercury or Venus, both work. And this angle has been known for thousands of years. What is the furthest separation that these planets are from the sun in our sky? And what the geometry dictates is that what that angle represents, what the line that's creating that angle, what it represents is the tangent line, the sight line from the circle of the planet to us. Okay, if this is the maximum distance that the planet can get from the sun, then this line, our line of sight, must be tangent to the circle. You can see that. It can't get any further. It wouldn't be tangent. If it's not tangent, if it goes inside, then it wouldn't be the maximum angle. The maximum angle, the furthest separation, is just when our line of sight just kisses the orbital circle of the planet. Well, this is a known number. This number has been known for thousands of years. And what it gives us is a right triangle, a theorem right out of Euclid. If a line is tangent to the circle, it's going to be perpendicular to the radius line. An elementary theorem from Euclid, which he uses. And of course, the sine of this angle is the opposite over the adjacent. If the math is unfamiliar to you because you haven't looked at this in 50 years, take my word for it that there is a simple mathematical relationship given this geometry. That's my point, okay? For you math types, you can see the math is very simple and very straightforward. Kind of takes your breath away, how simple it is. If you're not familiar with this stuff, the point I'm trying to make is given this geometric picture, once you buy into this picture, then very, very simple numbers that have been known from the sky watches way before Ptolemy starts to dictate what the dimensions and the sizes of Copernicus's universe must be. There is no wiggle room here. And the one that I rushed through that I wanted to take a look, because I think it's worth, again, making the point. The Mercury and Venus story is rather simple. This is a little bit more complicated. And as I watched the class last week, I realized that I did kind of rush through this, and it's not as complicated as I made it to be if I just take a little bit more time. So this is where I would like to start our class today. Here we want to find the distance out from the sun out to Mars. Jupiter and Saturn are exactly the same geometry, okay? Just the numbers he's going to use, the measurements that he uses will have different numbers to them. He starts with the opposition of the planet. That is, we have the Earth and Mars is on one side of the sky and the sun is on the other. And we go ahead and we wait until we get an elongation of 90 degrees, okay? From the new position of the Earth, turns out after 105 days, the angular distance between the new Mars and the sun is now 90 degrees. Why? Because that gives us another right triangle. And if we can figure out the angle here, this angle here, which I think I call A, if we can figure out this angle here, then we have another simple mathematical relationship, because the cosine of this angle will be the adjacent over the hypotenuse. And if we call this distance 1, the distance from the sun out to us, if this is 1, then we can go ahead and calculate the distance to Mars. Okay? Again, if the detailed math is not familiar to you, my point is that by taking this measurement here of 105 days, this is, we have no choice about what this number is. It takes a certain amount of time to get from opposition to the 90-degree elongation. It's a number. It's not going to change. No matter when you start opposition, no matter what tables you look at, going back from Ptolemy's tables, no matter what tables Copernicus has from more contemporary tables, this number of 105 degrees, everyone agrees on. It's a simple number to take. And from this number, given his geometry, it dictates how far Mars must be from the sun. There's no wiggle room here. Okay, and what I rushed through was I neglected to say that how you measure these angles is really very simple. If you have a central angle, that's an angle made from the center of a circle, then any angle is to 360 as the arc of that angle is to all the way around. Again, a theorem right out of Euclid. Any angle, any central angle is to the full 360 as the arc that it creates is to the distance all the way around. And so B is to 360, this angle here as the 105 is to the all the way around, which is the period of Mars, which he has taken from the synodic period. He now knows that it's 687 days. So it's a very simple proportion. B is to 360 as the 105 is to 687, and so he gets an angle for B. We do the same thing for the joint angle of the trip for Earth coming all the way around, okay? Earth goes all the way around, so A plus B is to 360 as the 105 is to all the way around. It's the same 105 days, so A plus B is to 360 as 105 is to 365 days. Again, another simple proportion in which we can calculate A plus B. We know B, we know A plus B, we can calculate A. And that was the goal. And the cosine of A is the adjacent over the hypotenuse. And from that, we can calculate the distance to the hypotenuse. And it turns out to be 1.52 of our distance to the Earth. There is no wiggle room here. These numbers are accurate because the measurements that they require are relatively simple to take. They don't take sophisticated telescopes to measure these numbers to a fair degree of accuracy, a couple of decimal points, 1 decimal point, and you'll get therefore these distances to 1 decimal point, given the fact that we're going to call the distance out from the sun to the Earth 1, which astronomers do. It's called 1 astronomical unit, 93 million miles, the modern number. That, of course, was not known to the people here in the time of Copernicus. So I wanted to just do this again to make the point, if I rushed it to some people who could have followed the math because they didn't do a good enough job. So I hope I filled that gap. And if you're not following the math in any case, then as I say, one more time, not to beat this to death, but the point is that given his geometry, as opposed to Ptolemy's geometry, given his geometry, he locks in the dimensions of that geometry very, very early on and very easily on, so that he does not have any wiggle room here. And so he's able to make the statement to the Pope that not only is my system beautiful, not only is it elegant and simpler, not only does it follow more fundamental principles, not only, but it is also so harmonious. It has such an internal integrity and harmony to it that you can't even fiddle with it. This thing is either right or you can throw it away. That's one of its great powers, because when you look at the numbers, you'll see that they are right. Okay, and that is his ultimate argument to the Pope and to the educated world in general. And here I wanted to show very fundamental examples of him backing that argument up with these kinds of numbers. Okay, and then we have the very impressive set of numbers of Copernicus compared to our modern numbers. And you can see how close they are because these measurements are not all that difficult to take. We have the orbital periods, and we have, therefore, we can calculate the orbital speeds. Speed is nothing more than distance over time. Here is the time, here is the radii, 2 pi r gives us the circumference. So the distance over the time will give us the speeds. And for the first time, we actually have objectively real numbers. What is the average speed of the planets as they go around the sun? These are numbers that Ptolemy could never produce. All he could ever produce was numbers relative to the dials that he has set at the time. There's nothing objective about his numbers. They're always relative to what he picks arbitrarily as some fundamental different size. What Copernicus says is, no, if you call the distance to the Earth 1, then these are the relative numbers. The speed of Mercury is 50%, 57% faster than when we go around. Okay? That Mars goes around at 80% of our speed, etc. These are objective numbers relative to the speed of the Earth. These are objective numbers with respect to the time it takes for these planets to go around the sun. If it takes us 1 year to go around, it takes Venus 62% of our year, 62% of 365 days for it to go around. These numbers are fixed, and they come right out of the geometry of his model. Also notice that he has shrunk by 50% the size of the solar system. He's brought Saturn in much, much closer. Ptolemy had a number of about 14, 15 Earth radii. I'm sorry, distances out from the Earth to the sun, distance out to the sun for Ptolemy from the Earth. Copernicus shrinks that down from 15 down to about 9. And then after that, Ptolemy, of course, immediately after that, has the fixed stars. Okay, important point we're going to make here. After that 14.8, right after that, soon after that, right behind it, are the fixed stars. Okay, so although the solar system here is bigger, Copernicus' system is ultimately much, much bigger because the fixed stars are way beyond Saturn. He needs this for the parallax argument that we'll get to in a moment. Okay, but I want to take a look at this picture. Let us take a look at this. Here are our two models. Here is the Earth in the center. Here is our ring of water and our ring of fire, and then we have the moon. And here is Mercury and Venus and the sun. And I just took one of the planets, and we have, of course, the epicycles and the deferents going around. And these are very, very important in Ptolemy's model. They actually create the whole phenomenon of retrograde motion. He needs, as we saw, the epicycles and deferents to actually create the fundamental motions of the sky, not Copernicus. Okay, here we have the sun in the center, Mercury and Venus. Here's the Earth with the moon going around. And again, he does use epicycles. He used them just to shape the orbits of the planets, to give them more of an oval shape so that his calculations would be more accurate. He does not use these devices to create the actual, for example, retrograde motion that we saw in the last week in the animation, where just when the planet sweeps around, Earth inside for Venus and Mercury, it sweeps through, going around faster. In that sweeping motion, the parallax movement against the big stars look like temporarily they're actually going backwards. Of course, it's just an optical illusion. So he's not using the epicycles in the same way that Ptolemy is. This is the fundamental geometry that you're looking at. The epicycles that he's using are much smaller. They turn much, much slower, and all they do is kind of shape the circular orbits to more of oval kind of orbits, very, very, small amount, so that he can get some of his measurements a bit more accurate. Fundamental difference. The geometry here of the concentric circles is essentially the same. As for example, this is the way most people thought of the current system. The system was just a bunch of circles going around the Earth. The difference in the, this is for the mathematicians. The basic idea was the Earth, of course, is in the middle of the universe, stationary, and the planets and the sun and the moon, everyone's going around the Earth. This is the fundamental truth that everyone understands. Okay, this is pure common sense that the Earth is stationary in the middle and everyone goes around us. Okay, this system here is very different. Here we have the sun now in the center. The sun is now stationary and the Earth is moving around. And I asked you the question, which is the computational device merely just to calculate where the planets are in the sky, and what is real? What's the real theory that actually explains reality? I ask you, and of course the answer is the system on the right. We know that this is the correct system, Copernicus system. This is what's real. Both of these are equivalent computational devices. They make exactly the same predictions. They tell you what the sky looks like a year ago and a year from now and everything else in between. Okay? They save the appearances. They are both pretty much to have the same level of accuracy. Not the greatest, but pretty good. They are equivalent as computational devices. But which one explains reality and which is just a computational device? We, of course, would say it's the system on the right. Everyone in Copernicus's time would say, what, are you crazy? The Earth is moving? The Earth is spinning and moving? We know the size of the Earth. I can calculate how fast I must be spinning in space if here I am, for example, somewhere in the Northern Hemisphere, okay? The equator is moving at about 1,000 miles an hour, spinning. If you were in Rome, for example, I think the number is 780 miles per hour that you must be spinning in space if the Earth is spinning once a day. Are you crazy? Of course, this is just a computational device. Everyone knows that the Earth is stationary. Everyone knows that the Earth can't move. How can the Earth move? What could move the Earth? You tell me a force that is powerful enough to move the Earth. I see what it takes to move, for example, the great bricks and stones when they build the cathedrals, the kinds of contraptions with pulleys and levers that have to be used to move those great stones. Then I go ahead and look at a mountain. What could move that mountain? What force could move that mountain? And you want me to believe that something can move the entire Earth? How absurd can you be? Clearly, this is what's real. Yeah, the details I leave to the mathematicians about the epicycles. I don't know. All I know is that the Earth is immovable in the center and the planets are going around. I leave the details to the mathematicians. This is what's real. This is purely a computational device. Clearly, as clear as the nose. However, we look at this and we look at the epicycles and the difference and the other devices. We say, well, this was a very clever computational device and it lasted for over 1,000 years. I give it a lot of credit. Okay, but how can anyone believe that that's what's going on up in the sky with the circles and the circles upon, and with the Islamic astronomers with the epicycles on top of the epicycle? I mean, come on, this is craziness. Clearly, this is not how the universe really is built. This beautiful, simple system of Copernicus, this is what's real. This makes sense. Okay? So I asked you to think about this, that in our mindset, given the paradigm that we have grown up with, the Newtonian paradigm, the one that we're getting to, we look upon the right side as real, and the left side as a computational device. At the time of Copernicus, he knew very well that the best that he could hope for from the general public is that it might be an equivalent computational device, and it would certainly not be taken as real, because this is as real as it gets. And that, guys, in a nutshell, is the scientific revolution. That's what we mean by a paradigm shift, that the educated general guy on the street can come to see something that is clearly real and what reality is like in the universe, and find a way to reject that, and in fact to see it as just a crazy kind of computational device that who could possibly have ever, and to move over to something which clearly can't be real because, well, you have the Earth moving. End of story. You know, this is in a nutshell what we mean by a paradigm shift. Okay, and the fellow who took over for Copernicus actually brought this to publication. Copernicus was very, very ill when he finally let people go ahead and bring this to press. It was done by the man by the name of Osiander, and he was turns out a Protestant minister, and he wrote a preface to try to protect Copernicus from the slings and arrows of the people who would make fun of him and tell he was crazy, because he said, you know, when you read this book, it doesn't have to, not even plausible what he's saying, but it is, you'll find a very, very useful computational device. And this is not at all what historians of the science are very much convinced unanimously that Copernicus did believe his system was real. He would not have worked on it the way he did for just a mere computational device. For all those reasons that we gave about him having to reject so many of the devices of Copernicus, too radical, too beyond the basic premises of Plato and Aristotle, he was looking for something that was, again, that he could call real. And he had the ability to just go outside the box to a moving Earth. But once he got there, then the rest of everything fell into place. And so the thought is that this preface was written to try to protect Copernicus, not to hurt him, not to disparage his work, but to take what only that could be accepted in the minds of him, the writer, and every other educated person. Clearly, this is just a clever computational device. And by the way, if you're interested in the preface, it's a very famous piece of work. This letter, this preface that's in front, is in those writings that I sent you last week in one of the Word documents. Let me stop here because this is one of the great points that I wanted to make about theories and how theories can describe. Certainly a theory must describe what we see, but does it explain? And how, when you look at these two pictures, how you can flip from one describing and explaining and the other one only describing to the exact opposite. How does that happen? How does that happen? Any comments or questions before we move on?
Peter, one comment and one question. The comment is, boy, it's remarkable that at this time they're able to calculate the ratios of the distances of the planets in terms of astronomical units, and yet they don't have the underlying distances. I'm used to thinking that it works the other way around. That first we get the this easy, quote unquote, easy to measure stuff, and then establish the ratios. But this is very elegant. The question is, what did they have as a model commonly? What did the scientific community have for what the planets were? I can see that it was very difficult to imagine what force could move the Earth, and yet they are perfectly happy with Jupiter and Mars being moved.
I'm very glad that you asked that question, Mike, because it's very good for me to review. I gave you that answer, but I've been throwing so much information at you guys that you can't absorb it all. So I'm very glad that you asked that question, because it's a great question if I didn't have an answer for you so far. But if you recall, the answer is that the planets are made of a fundamentally different substance than Earth, air, fire, and water. They're made of the ether. There's this divine substance which has no weight. It does not have the properties, any of them, of Earth, air, fire, and water. Okay? The ether has only one property, and that is that it moves in perfect circles at constant speeds. And that's what the moon and everything above the moon is made of. And that's why they move so easily, because that's what they do. Just as heavy things fall down, straight down, because that's what heavy things do, what the ether does is it moves in eternal circles and combinations of circles at constant speeds. And that's the answer.
And I guess I brought my preconceptions to it. I had thought their model was that
exactly. You of course, yes, you of course have the Newtonian paradigm. We all do. It is very difficult to come back and see this as a paradigm, as something that's in your mental furniture, that you work within these kinds of concepts and categories. This is what the scientific revolution is all about. This is why it is so important in intellectual history. Okay? It is the first time that this has ever happened. This is the first, and it has been studied more than probably any other paradigm shift. There's been more written about the scientific revolution by historians of science and other historians than probably any other, certainly scientific event. We have gone through, we're told that we have gone through a second paradigm shift with the quantum revolution, but we are still in the middle of that. As we'll see as we progress through our story, it takes a long, long time, many generations for this shift to happen. Our shift to the quantum paradigm has not happened yet. We are still very confused by the duality of particles and waves. What the heck is that about? And then you start talking to me about entanglement. I've read about entanglement a million times and I still don't understand it. That's because it's very difficult for us to break out of our Newtonian classical physics paradigm. Okay? There was a minor paradigm shift by Darwin, okay, in the world of biology. People are still fighting that. It's only been, what, 200 years? Hasn't been enough time for everyone to get on board with evolution. They're still fighting that paradigm shift. Very, very interesting cultural and intellectual phenomenon. And that's why the scientific revolution is so interesting, because it is the laboratory to understand how that shift takes place. Most people don't believe that the sun is, that the earth is not moving in the center of the universe. Most people, most people have moved away from the classical paradigm. Okay, and so the shift has truly taken place. And how does that happen? Is a very, very interesting story. And that's, of course, our story. That's what we want to do for our last 4 classes, is to go through that story. But just before we leave this picture and the contemplation of it, how are we going to make a paradigm shift? Well, one thing that you could do is you could begin to disparage the theory on the right. You could start to show that the theory makes predictions which are wrong, that it has assumptions which we can demonstrate are truly wrong. That's coming. Okay, that's actually going to come today. We can also find a way to maybe tweak the system on the right, make it more accurate. So not only make it more accurate than the old system, but to truly make it more accurate against the sky, that it doesn't drift away from the actual what's happening in the sky 10 years from now or 50 years from now, that the model continues to hold up. Its accuracy continues to hold. Ptolemy's system never did that. Copernicus' system will never do that. But maybe we can tweak this system on the right, keep the fundamental idea the same. What's the fundamental idea? That the sun is stationary and all the planets, including us, go around it. That's it, isn't that? That is the bottom line. When you take everything else away, what you have here, what Copernicus is telling us, is that the new reality is that the sun is stationary and all of the planets, including us, somehow or other go around it. If we can modify that model to be more accurate, that would be a help in changing the paradigm shift. But it's not going to be enough, because you go back to the left-hand side. I can't get around the fact that you've got the Earth spinning and turning. And now, the turning, going around the sun, that's got to be incredible. That's got to make the spinning look like small potatoes, because we know, how far away the moon is. I mean, we know, we've measured how far the moon is. The moon is 60 Earth radii away. We can imagine how far away the sun is from the Earth. And you're telling me I go all the way around that circle in 1 year? How fast is that? It's about 30,000 miles an hour. Not 1,000 miles an hour, but 30,000. I'm flying through space at 30,000 miles an hour while I'm spinning at are you crazy? You can see that to create the paradigm shift, yeah, you can disparage the old systems. They'll tweak it. Yeah, we'll see that today. They'll tweak the old system to get around some of those problems of when they begin to dismantle some of the assumptions. We'll go ahead and improve the right-hand side. Kepler is going to do that with its new laws, become very, very accurate, to make predictions that will be unprecedented in history in terms of their accuracy. But you're not going to make the paradigm shift until you can get rid of the reality of the left-hand side, that the Earth is stationary and everyone goes around the Earth. Until you can convince people that that is not true, that in fact the sun is fixed and we are spinning and turning around the sun like everybody else. Until you can convince someone of that, all the details don't matter. No one is going to move away from the fundamental reality. Who does that? Who does that? Who makes the intellectual world begin to make that shift? That's Galileo. And that's why Kepler and Galileo are the two central figures of the scientific revolution. And who finally marries both together? Who shows that Galileo's new dynamics his new notion of motion can be married to the better model of the solar system, the more accurate model, who can marry those two together? That's Newton. And that's why Newton is Newton. Okay? And that's our story. I've just given you the story. I've just given you the punchline. But let's go ahead over the next 4 classes and look at the wonderful, very, very interesting and beautiful story of how it unfolds, this story of discovery. Okay, to quickly finish up Copernicus, he is truly the founder of modern astronomy. He does create a simpler, more harmonic system. He integrates the planets into just one coherent system, which the Almagest never did. But what he does is he's trying to change our fundamental point of view. He is not successful, but he changed his fundamental point of view of the Earth being out there with the rest of the planets. We're no longer protected here in the center by God's creation. We are out there floating like everybody else. It's a terrifying idea. Okay? And along with that terrifying idea is he tremendously expands the size of the universe. He pushes the celestial sphere out to unimaginable distances. All of a sudden, we don't have this blanket of the cosmos around us to protect us that was created by God so that we would have a platform so that we could earn our right in heaven. All of a sudden, that's now shaken because just what is all this distance about? What is all this incredible empty space about? Why is there such incredible space between Saturn and the stars? How does that make any sense? What is the purpose of that? Why are we so alone here in the universe? Why would God do such a thing? I would not do such a thing. How can that make sense? And of course, the model goes on to explain the fundamental ideas that we did, the varying brightnesses and retrogrades, etc. The only ad hoc assumption that he has to make, the one he has for you to accept, he doesn't ask you to accept the fact that Mercury goes around the sun in 88 days and is 43% of the distance out to the sun. He doesn't ask you to accept that. He has measurements for that. He says, if you accept my geometry, then those numbers are fixed. You either like them or you don't, but they're fixed. What he does ask you to accept is that we can see a parallax of the stars, even though we're moving at a great distance from January to June, from one side of the sun to the other. We move across a tremendous baseline. We can see no difference in what the stars look like. How can that be? Copernicus, how can that be? I mean, we've been making maps, for thousands of years. We know about how to triangulate distances, great distances. We know this by measuring different angles. How can there be not a different measurement of angle from January to June of the fixed stars if you're right that the Earth moves so far in those 6 months in space? Copernicus says it's because the stars are so far away, we don't notice it. Oh, well, that's very convenient for you, Copernicus. Talk about self-serving arguments. My goodness, give me a break. No one accepted this idea at first, that the stars were so far away, that the cosmos was so much bigger than anybody thought inside the paradigm. Such an incredible break. So if you're looking for the revolution in Copernicus, the revolution is in 2 places. He has the ability to see that the Earth moving, the whole system makes a lot of sense. It makes so much more sense if you put the Earth moving. Admittedly, as he says to the Pope, it's an absurd idea. But if you give me a chance, I'll try to make it understandable. That's his first radical idea. The second radical idea is the explosion of the size of the universe itself. The size of the celestial sphere is not 10 times bigger, not 100 times bigger. Who knows how much bigger it must be for us not to be able to detect the paradox. These are his two great revolutionary ideas. Neither one of them accepted at his time. Not in this generation, not in his next generation, not for a while. That's going to be our story. But if you're looking for the revolutionary in Copernicus, that's where you'll find it, in those two places. Okay. So the weakness of the theory, of course, is, first of all, there's no convincing explanation of the moving of the Earth, certainly. It's not any more accurate than Ptolemy's Almagest. It has no new evidence to support the theory. There are no new discoveries about the sky. Copernicus knew nothing more about the sky than Ptolemy did. Okay, he had no new discoveries. They're coming. Okay, and of course it predicts that there must be that there cannot be a detectable parallax. There isn't any. He doesn't predict that. Everyone knows there's no detectable parallax. The astronomers go look for it. They want to give them half a chance. They go look for the parallax and they don't find it. And he says, well, that's because the universe is so large. We can't detect it. And the other one, the real killer, is that there's no explanation of how the moon can keep up with the moving Earth. See, everything is fine if the moon is stationary. If the Earth is stationary. If the Earth is stationary, well, that's fine, right? Everyone's going around the Earth, no problem. All of a sudden, you got the Earth moving at these incredible speeds, and the moon somehow or other can keep up. How does that work? How does the real moon keep up with the real Earth when it's moving? Okay, a real problem. The picture down below is an example of the parallax argument. Okay, if the Earth has a tremendously great distance between two stars, you would think that there would be an angle change. When it's very, very far away, the angular separation would be smaller than when closer. But we do not see this angular change. Why, Copernicus? Why don't we see this? Because these two x's are not here. If you want to call this 1, this is not 1.5 like this picture is. This is not 10. This could be 100 compared to this distance here of 1. And that's why we don't see it. And I'll show you an animation of that in a little bit. So those are the weaknesses of the theory, and they truly are. These are true weaknesses of the theory. You can appreciate these weaknesses from inside the old paradigm. And the conflicts with the Aristotelian physics, going back to Mike's question about the ether, well, again, just to restate, if the Earth is moving like a planet in uniform circles, then isn't that a violent motion of the Earth and the water? What's going to move the Earth? What could create the Earth to have a violent motion? How do you move the 800-pound gorilla? And if the natural motion of the Earth is circular, want to go that way, okay, want to play it that way with me. If they move circular, their natural motion, because what could move the Earth, right? Clearly it must be just moving naturally, then it must be like the planets. So what about the difference between the ether and the Earth, air, fire, and what happened to that great difference if everyone's moving in circles? What happened to the great distinction that we all understand as common sense? What happened to that, Copernicus? If the Earth's not the center of the universe, what do things fall down to the center of the Earth? What's this business about? What's so important about this rock going around the sun? Why would things fall to the center of this moving rock? The Earth is no longer important anymore. There's nothing special about the Earth anymore. Is that right? If I understand you right, Copernicus, there's nothing special about us anymore. So why would things fall down to its center? And, talk about the absurdity of the Earth moving. What about, how can the clouds keep up? How can the birds keep up? Why don't we have this incredible wind that we feel? The air can't keep up with this moving Earth. It must be blown away. We must have, there's got to be chaos. We would be surrounded by chaos if the Earth was moving the way you say it's moving. How could the... Notice all these arguments, guys, are about motion. They're not necessarily about astronomy first. They're about motion, about how different things move and why. And this is why Galileo is so central to our story, because he's the one who tackles these questions. He's the one who diffuses these conflicts. And it'll become really the heart of our story, truly. The heart of our story is still coming. because we have not yet seen how the paradigm shift is made. Of course, you can imagine all the clerics were not crazy about this idea, being against Scripture. Turns out it's funny that the Protestant Reformation, the Protestant ministers had more trouble with it than the church did. I think Copernicus did a pretty good job. He was a member of the church. He was a very devout Catholic. He showed great respect to the Pope. He tried to say, there's the preface from Ozymandias, saying that maybe it's just a calculating device. Don't take this stuff too seriously. So the church didn't really worry about it too much. But it more upset some of the Protestant clerics than it did, ironically, the Catholic clerics at the time. And the reception and the aftermath. It's going to take generations for these ideas to begin to bleed into the culture, into the educated culture, which, remember, is a very, very tiny percentage of the population of Europe at this time. But people did begin to create tables from his geometry. People making tables ever since Ptolemy's time, ever since Hipparchus's time. They were making tables of positions where you could predict future predictions from the tables. That's what the astrologers want. They want this, I don't care about the deference and the others. Like, just give me the tables, please. Show me the tables. That's what I need to do my job. And tables began to appear using his geometry by some of the very famous astronomers of his time. They didn't believe in the theory. Okay, they saw that it's a lot easier. The math is easier using his geometry, and it does give equivalent answers. So why not? It's a wonderful calculating device. Let me go ahead and use it. Okay, even the Pope, when he called the scholars to do calendar reform, when it finally did take place under Pope Gregory, and they did change the calendar where they made the leap years better and everything, moved away from the old calendar of the Caesarian calendar, they actually used Copernicus's tables again because they were just easier to use. They gave equivalent numbers, so why not use the easier calculating device? So within this 100 years from Copernicus up to the time of right before Newton, to the time of the death of Galileo and Kepler, in that time frame, people began to understand what this theory was about. Like, we understand quantum theory, like we have some vague idea of why particles can be waves and waves can be particles. And we read, we try to understand this stuff. We watch Nova shows. We hear explanations by scientists to try to break it down, give us metaphors. This is what was going on. A lot slower, of course, and for a much smaller percentage of the population. People were trying to at least understand what Copernicus was saying, as crazy as it may be. And it began to take hold with some, anti-establishment kind of thinking. And it really didn't cause a problem. It really didn't get thrown on the index of forbidden books until that troublemaker Galileo comes along and start pushing his fingers into people's eyes, poking at people and saying, no, this is real. No, whether you like it or not, this is real. And no, Galileo, wait a minute, hold on. You're telling me I got to believe this is real? No, we're not going to go for that, okay? We'd rather throw you in jail than go for that. And we'll see that as part of our story. Okay. So one more look here at theories, right? As we think about this progression of going from one paradigm to the other. Most of these ideas we've come across already in our discussion so far, but all these ideas, guys, come up in the next generation or two. All these ideas now bubble up and say, hey, wait a minute, what about this? What about that? Every single one of these that I'm going to read to you all surface as a question. Well, if Copernicus is right, then what about that? Wouldn't that follow, etc.? And this is what good scientific theories do, of course. They raise new questions. Okay? We'll see, as we look maybe a little more closely, not today, that Aristotle's theory of motion raises no new questions. Ptolemy's system never raised new questions. It raised the desire to twiddle the dials and the buttons. It didn't raise new questions as to what was going on. The paradigm was fixed and static, and it was not It was what it was. It did the job. It answered what we needed to know. It did not raise new questions. Copernicus's ideas definitely raised new questions, and here they are. You can calculate that Rome spins at 780 miles per hour, and the sun goes around the sun at 3,040 miles per hour. How could the Earth move so fast and we not feel it? What force could move the Earth? Why do heavy objects fall down to a spinning Earth? How can the moon keep up with the Earth? If the Earth is just another planet, and the planets are made of the same substance as the Earth, then maybe there are creatures on the other planets. Yeah, people began to think about that. If the distance from the sun to the Earth is tiny compared to the distance of the stars, what's the purpose of all this extra space from Saturn out to the star? What's the purpose of it? What's God's plan about all that space? What's he going to do with it? Why do we need it? Maybe the sun is just a large burning sphere. Maybe it's not ether. Maybe it's just some very hot, glowing, burning thing. Maybe it's a lot simpler, because what's with the ether? I don't know about the ether anymore, but maybe the sun is just this burning thing. And if the sun is just a burning thing, burning sphere, then maybe the stars are the same. Maybe the stars are just burning suns that are much further away. And if they are just suns kind of like our sun, maybe do they have planets revolving around them just like we do? Yeah, these are all speculations that grew in the next generation or two after Copernicus. And if the celestial sphere doesn't move, well, why have the stars fixed to it at all? Why did the stars have to be fixed to something which is not moving? Right? Maybe the stars are at different distances. Maybe they're scattered all throughout the sky. Maybe the cosmos is in fact infinite. Maybe the stars go out forever at different distances, now that they're no longer fixed and painted on one sphere anymore. Copernicus tells us that they're so far away. Well, maybe there's no bound to how far away they are. Yeah. And finally, just to get to that Darwinian kind of change, that very terrifying change when you're inside a paradigm. If we're just a rock revolving around one of many stars, then why did God create us so uniquely? What is so special about us? Are we really special after all? Or are we, I don't know, just alone in this terrifying new image that Copernicus has given us of this empty, open space where we're no longer special, we're no longer protected, we're no longer watched over, we no longer have a plan that's all about us. The plan is all about us and supporting us so that we can be happy forever. That's what the whole point of everything is. Copernicus' system doesn't seem to be that. It doesn't seem to give me that kind of comfort anymore. In fact, it's quite terrifying the more and more I think about it. How do you move people into such a terrifying new paradigm? Right? How is that done? Okay, let's switch to Tycho and Kepler. Questions while I make the switch. Questions, comments?
I have a question.
I'm sorry. Go ahead.
Yeah, sorry, Peter. I have a quick question. The term universe, I'm wondering when that started to come into actual use. We know
Thank you for asking. That is such a wonderful question.
I mean, prior to that, it was probably firmament, which means firm and fixed. But when did universe start to be used?
Yeah, the universe goes back to the word cosmos, which is part of the Pythagorean tradition, that the universe was everything, the cosmos was everything, and everything had a harmony to it. It was all put together by a mathematical harmony, mathematical structures. And it's the idea of the cosmos which developed into the notion of the universe being everything physically all described together as one thing. But that one thing had to be in people's minds. And the first idea of that was that unifying cosmos. And so the cosmos bled into the universe.
Thank you.
Peter, Tuesday night, we were to look at the stars to see the alignment, or not the stars, the planets, the alignment of the 5 planets.
Yes,
And here in Peterborough, it was cloudy, so we didn't see it. But
yeah.
after dark, I saw one very, very bright object. Would that
You
have
know
been
what that,
Venus?
you know what that was, don't you?
Is that Venus?
Absolutely. Can
Yeah.
only be.
It was,
Only,
it
it
was
is by
beautiful.
far, it is by far the brightest star in the sky, but there's nothing even close as a star. There is nothing even close than Venus. Venus is so close to us, and it has that shrouded cover of those clouds all around it. And so when the sun hits those clouds of Venus, it just lights up like a beacon. Yeah, beautiful.
Sparkled like a diamond.
Yes,
Diamond in the sky.
yes. It is the first star that you'll see every night. It's the first star that will burn through the haze, burn through the twilight. It is the first star to make a wish on, for sure. Okay, we only have 15 minutes. I want to see if we can get through Tycho. I want to move through Tycho quickly. There are other places where you can take a look at Tycho. There's the article in the Scientific American about the Uranoborg. There's the video on Kepler that talks about Tycho's work. So let me go through Tycho quickly, and then next week we can do Kepler and then move on to Galileo. Tycho is the greatest natural naked eye astronomer of history because of the instruments that he uses and because of his passion for precision, of measurement precision. And he begins to make these discoveries because of his position, because of his instruments that he uses. He begins to make discoveries which begin to dismantle the paradigm, dismantle the cosmos as was understood. And the first one is this first nova, supernova, we would call it now. He called it a nova. We call it now a supernova, a new star. In 1572, that was in the constellation Cassiopeia. Here's a modern picture, and here's where the new star was. Here's a picture from his book where he talks about the nova, and here is his new star. Here's the W of Cassiopeia, and you can see he measures I as the new star, the nova star. And he's able to show that this is truly as new. This is not an atmospheric thing, a blip that comes out. This star is visible for 18 months. It is a supernova in our galaxy. It's very close to us. These are rare. Supernovas are happening in the universe all the time, but very few happen in our galaxy. And we were lucky enough to get one at 2, actually, in the time of the scientific revolution. And Tycho was able to show that this is out there, way out there beyond the stars. This had no parallax. This was up in the stars. Well, we always thought that the ether was all eternal and unchanging. Here's something brand new in the ether. Here's a new ether that bubbled up out of nowhere. Maybe the universe is not as unchanging as Aristotle claims that it has to be. The first little chink in the armor. And here's the famous Uranoborg, the island that he gets. Very fascinating. He creates the first really research center of the world, in the sense where every astronomer, every mathematician wants to come and work for the famous Tycho. As his career progresses, he does become the most famous astronomer in Europe. In fact, the most famous scientist, if we can use that modern word, in Europe. And everyone wanted to come to Uranoborg and work with him. And he basically trained the next generation of astronomers. And just to give you an idea of the accuracy of his work. See, before Tycho, people took measurements. Certainly, there are plenty of measurements in Almagest. There are plenty of measurements in Copernicus's work, but they took important measurements like oppositions and things like that, and special kind of events that could be useful. No, Tycho took measurements every night after night for 20 years. If there weren't any clouds, he and his staff were out there taking measurements of all the planets. And he didn't take one measurement. Tycho took 3 measurements from 3 different places on the island. He had posts where he had his staff take 3 measurements and then take the average of those measurements. He was using methods that were far beyond he invented, new ways of taking measurements. First time we see this kind of emphasis on precision and measurement. Not surprising, it's coming from a mathematician, from an astronomer. It's not coming from the philosophers, from the people who are, working on the ideas of the paradigm. Where was measurements? Measurements were for artisans. They were for builders. They were for merchants. They were people who sold things. And that's where people took measurements. It wasn't for philosophers who were trying to understand the fundamental ideas of the universe. No. But the mathematicians began to take measurements, and Tycho showed us how to take measurements of accuracy, unprecedented in history, the best that could possibly be taken by the naked eye. It is now understood that when you look at his measurements, you cannot get more accurate than he with the naked eye. His measurements were about 2 minutes of arc, right? There's 60 minutes in a degree. So he could take 1/30th of a degree, 360 degrees in the circle, 1/30th of a degree. That's the distinction he could make with his instruments. And you can see the incredible accuracy of the precession of the equinox, right? The place where the sun on the ecliptic crosses our equator, thrown out to the sky, the celestial equator. That place is the first day of spring. Well, you look at what stars are behind the sun on our spring equinox. That place begins to drift very, very slowly. It's been known since the time of Hipparchus that the place where the sun just crosses, the ecliptic just crosses the celestial equator, the stars that are behind it seem to drift. That is the point where the sun is, drifts very, very slowly. Just 51 seconds of arc in a year. Okay, less than 1 minute of 1 degree. Tycho took that measurement to be 51 seconds of arc. The modern number is 50.23. This is measurements beyond anything that Ptolemy or Copernicus could even dream about. They would never contemplate being able to take such measurements. It's out of the realm of possibility. Tycho made it possible with these kinds of instruments. Very fortuitously, we had a wonderful comet go across the sky in 1577. The whole world saw it. It was a sensation. It had a tail of 20 degrees across the sky. Everyone came out every night to look at the comet. It was talked about by everyone, and Tycho was able to show that this comet had no parallax. He was able to actually track its orbit. Here's from the book that he wrote. He wrote a book about the comet, and here's the Earth, and here's the sun, and here is him tracking the position of the comet as it moves around the sun, okay? And what is it doing? It seems to be crashing through, the orbits of Mercury and Venus. The comet is crashing through the crystalline spheres. You're not supposed to be able to crash through the solid crystalline spheres. First of all, there's supposed to be nothing new in the, well, we got rid of that with the nova. Well, comets, they're just atmospheric things. They're like shooting stars and comets. They're things in the atmosphere. They're below the ring of fire. They'll come and go. They're parts of earth, air, fire, and water. No, Tycho says, this is beyond. This is up in the ether. And this new piece of ether is crashing through the crystalline spheres. So much for the crystalline spheres. They're gone. Okay. Tycho, with his accuracy, is able to measure the parallax of Mars. Okay, he knows astronomers all around the world. He's trained half of them. He knows astronomers from Britain all the way to Turkey, and he'll go ahead and take the night where Mars is at opposition, where at its brightest, there at its closest, and he'll ask the astronomers from Britain and Turkey to take a measurement of Mars at the same time and report back to him. Yes, Tycho, of course. Of course, we would be very happy to do that. And what the astronomers on one side of the Earth on that given night compared to the other, so many thousands of miles away from Britain to Turkey, show that the astronomer from Britain sees Mars behind this star, and the astronomer from Turkey sees Mars behind this star, and they see a parallax of Mars. Okay. You cannot see a parallax of the sun. This picture is not the scale. As you know, the web is full of bad science. We know from Copernicus that this is a half of this, right? The distance out to Mars is 1.5 Earth radii. So this looks more like a quarter. If this is 1, this distance should be about out to here. All right, be that as it may. Fact is that he could detect the parallax of Mars. You cannot detect the parallax of the sun without a telescope. So it's very interesting that Mars is closer than the sun. You can detect the parallax of Mars, can't detect the parallax of the sun. Mars is closer to the sun, to us. Mars is closer to us than the sun in opposition. Therefore, Ptolemy is wrong. Look at Ptolemy's system. Mars is always beyond the sun. Here's the Earth, here's the sun, here's Mars. Mars is always further away than the sun in Ptolemy's system. Not true. Tycho, by his measurements, by his precision, is able to make discoveries and predictions which are beginning to dismantle and reject the Ptolemaic system. It's okay, be all right, we'll fix it. This fixes. This is not the end of the story, not by a long shot, but this is wrong. This is wrong. Okay, there are new things in the cosmos. There are no crystalline spheres. I don't know what the heck is keeping up these planets anymore. I don't know. It's not these solid spheres of ether which are carrying around. That's not true, but they are there. I don't know what's carrying them around, but definitely this picture is wrong. Mars is closer to us in opposition. And this never shows that, as Copernicus does. In opposition, Mars is closer to us than the sun is. Yeah, Copernicus has it right, and Ptolemy has it wrong. We reject this. Not completely, okay, because the Earth is still at the center of the universe. The Earth is not moving. We all know that. We got to find a way to fix this. We will. Tycho wasn't happy with Copernicus either, because he went out to look for the parallax of the stars. All right, Copernicus, we'll meet you halfway. You're telling me that the stars are so far away that it's very difficult, impossible, not noticeable to see the parallax that should be there. Well, I'm Tycho. Okay, I've got instruments that no one has ever had before. If there's parallax, I'll see it. Trust me, I will discover your parallax if it's there. Okay, let's, maybe some crazy reason that you are actually right and these stars are so far away from. I'm not saying that the Earth is not moving. I'm just saying that maybe you can detect this parallax. Who knows? I'll give it a try. And he can't find the parallax. He says, well, come on. Here I'm looking in the winter, I'm looking at the summer, right? Going across this great orbit, you're telling me that the Earth moves in. Okay. Let's say I look to my left every time. Here in January, I'll look to my left to see the star. Let's say he's looking at Sirius, brightest star in the sky. Okay, so he's looking at Sirius, and he looks to his left, and he sees this angle here. He waits around to the summertime, and he again looks to his left, and he sees this angle here. Clearly, these two angles would be different. This angle would be very big, this angle would be smaller. These two angles would be different, and that would be the parallax. He would notice a difference in these angles when he looked both times to his left from his baseline of the moving Earth. He did not see a difference in these angles. Let us see. What he was looking at is this. Here's the sun, here's the Earth on either side, and here's the star. And clearly, if you look to your left, you will see a very, very different angle if the star is close. Very, very noticeable, very easy to see. Tycho certainly did not see this difference. The red angle would be 135 degrees, the blue angle would be 45 degrees. But look what happens if the star is further away. As the star gets further and further away, look what happens to those angles. Yeah, those angles start to get closer and closer together. Instead of being 90 degrees away, they're only 11 and 12 degrees away. This is not so easy to see. Tycho would say, 11-degree difference? Come on, I can easily detect an 11-degree, and I did not see an 11-degree. I didn't see any difference at all. And my instruments are the best in history, and I didn't see it. Yeah, I get that it's difficult measurement, but come on. How far away could Sirius be? I mean, let's get real here, okay? Well, Sirius turns out to be 8 light years away. And here, that means if this distance here is 1, if 93 million miles is 1, if this is 1 AU, then 8 light years away is, I did the calculation for you, is 500,000 AU. Yeah, it's 500,000 AU. This picture is not, what Tycho was dealing with was not 10 to 1, it was 500,000 to 1. That's what he was dealing with. Of course, he did not realize that. And that's why these two angles are virtually 90 degrees. The distance to Sirius, the rays are coming in virtually parallel. And his devices could not see it. It took 200 years of telescope development until the 1830s before finally telescopes of the 1830s could see this difference. Tycho inside the paradigm could not accept these kind of distances. He understood that you would have to have these kind of distances, something like that, if his instruments couldn't detect it, couldn't go there, that's crazy. So therefore, it was not detectable at all. Okay, so I think we're just about to wrap up, Tycho. To see if we can get through. So he rejects both Ptolemy and Copernicus, and he solves the situation. Okay, we're not going to give up on the paradigm so easily. My goodness, what kind of scientists will we be? Let's find a way to save the appearances by keeping what's real. And everyone knows what's real is that the Earth is fixed and everyone goes around the Earth. That's what's real. Everything else is, you know, let the astronomers worry about that. Well, I'll worry about it for you. We'll keep the Earth fixed. We'll have the moon go around the Earth. Everybody agrees to that. We'll have the sun go around the Earth. All right, Copernicus will let the sun go around the Earth. And everyone else will go around the sun. Okay, Copernicus will meet you halfway. All the other planets go around the sun, but the sun goes around the fixed Earth. And here we have a system which is completely equivalent to Copernicus. This is mathematically equivalent to Copernicus. Okay, all you've changed is the center of the origin. You change the center of the origin from the fixed sun back to the fixed Earth. Everything else is the same. Okay, and this will save this is equivalent to Ptolemy's measurements and Copernicus's measurement. This will give you the same sky. Now with Copernicus, now with Tycho's better measurements, so you even get a better set of dials to fool with. Okay, and this system keeps everybody happy. And as the astronomers begin to move away from Ptolemy, they move towards this because this is real. This keeps the Earth fixed. This keeps Aristotle's physics intact. Notice the orbit of Mars. The orbit of Mars needs to go through the orbit of the sun. The orbit of Mars needs to go right through the orbit of the sun, giving Copernicus's measurements that Tycho agrees with, that these are the right distances from the sun. He completely agrees with Copernicus on that. And so he has Mars breaking through the crystalline sphere of the orbital orb of that's carrying the sun around. Tycho says, no problem, there are no crystalline spheres. I don't know what's keeping these planets up. I don't know why they go around. Copernicus tells, Aristotle tells me they go around because that's their nature to go around. They go around as naturally as a ball falls down from my hand. That's why they go around. I don't know what carries them. I don't, but they certainly do go around. And this will preserve what's real, which is the Earth is fixed and everybody goes around us. and the stars are close as they always were. And we have our contained cosmos, and everyone is happy for a while, and everyone can forget about the reality of Copernicus and use it as a calculating device if you want, and all is right with the world. Until he hires this young guy, Kepler, who will turn everything upside down again. All right, guys, that's our class. Any questions before we go?
Thank you.
Questions, comments?
Yeah, thank you also.
All right, guys, I'll let you go. I'll see you next time.